Okay, so what we're working on today is heating curve. Yesterday, we talked about an introduction to heating curve. That video is online. We talked about the equations, but we didn't actually do any of the equations. Today, we're doing the equations. So, first thing is at the top of the page, every factor that you need given to you is here. Okay? So, one of the things I want to point out to you is the specific heat capacity. I want you to notice something about the specific heat capacity. Every substance has a unique specific heat capacity for each phase of matter it's in. So you have to pay attention to that. Okay? The other thing is, if you remember, I told you we're going to do all of our delta H's will be in joules per gram, so you won't have to do any metric conversions and you won't have to do any mole conversions. That's not saying that you won't have to do any mole conversions in stoichiometry or in thermochemistry, excuse me. There are some questions that show up on the homework where they'll give it to you in moles and you'll have to convert that into grams to find out what you should be doing. Now, this is a heating curve that goes from minus 10 to 110. This is a 100-gram sample of water, as you'll see right here. Our questions are breaking it down segment by segment. So we're starting here, and we're not going to finish until we get up here. Here's the problem that people will have. They'll say, I have 100 grams. The specific heat of water is 4.18 joules per grams degrees Celsius. And we're going from minus 10 to 110, so that's a 120 degree change. And they will plug that all into Q equals MC delta T. And they will be wrong. You cannot take a shortcut. If I'm going from minus 10 to 110, that means I'm starting in segment A, I'm ending in segment E, so I need to have those two equations, and then I need to have an equation for every segment in between. So this one is a 5-step problem. Does everyone understand that? So when I tell you that you have a problem, you should plot it on a heating curve so you know how many steps you need to have. You need to do that. Okay? We're going to go through 5 steps, and then I'm going to leave the problem at the very end for you, which is a 4-step. And let's see if you guys can figure that out. Okay? So we're going to start with segment A. What phase or phases are present in segment A? What do you guys think? It's a solid. All H2O below zero will be a solid. Is the energy absorbed from the heat source changing the water's kinetic energy or potential energy?
Potential.
Why would you say potential, Hugo? Does anybody think the other way? Nobody's going to go out on a limb on here. Tell me, what is changing in segment A? Temperature is changing. What is the definition of temperature? Anybody remember what the definition of temperature I gave you? It should be in your notes. What you got, Griffin? The average kinetic energy of a system is temperature. In this segment, temperature is changing. So what are we changing with this energy? Kinetic or potential? It's this kinetic energy. How do I know it's kinetic? The temperature is changing. Since that is the definition of temperature, it's always going to be that way. Everybody cool with that? All right, next one. What phase change, if any, occurs in this segment? Is there a phase change between minus 10 and 0? No, there's none. What equation would we use to find the heat for this segment? What equation will we use to find the heat for this segment? Momo? Q equals MC delta T. How do I know that we're using Q equals MC delta T? There's a change in temperature. If there's no change in temperature, the delta T would be 0. We don't want to multiply anything by 0 because that would indicate we're not using energy. But we're adding energy the whole time. Okay? So we cannot say there's 0 energy being added. There's always energy being added here. All right, so what is the amount of heat energy absorbed? The mass was 100. The specific heat of ice is 2.09. The change in temperature is 0 minus minus 10. What is anything minus minus? It's plus, right? So I'm increasing by 10 degrees. So 2.09 times 100 moves the decimal 2 places to the right. Times 10 moves it 1 more place to the right. So I have 2,090 joules for segment A. Is everybody with me on that? We're all frosting the same cupcakes? All right. We're now in segment B then. What phase or phases are present in segment B? What's happening in segment B? Something's happening. The temperature's not changing, so what must be changing? Griffin? It's going to be solid and liquid because it's the melting point. This is the point where we're going to have a phase change occurring. So both the previous and the next segments will be present. Okay. Is the energy absorbed from the heat source changing the water's potential energy or kinetic energy? This potential, why is it potential? It's just what Ian just said. Nothing's changing there. The temperature's not changing. So if temperature's not changing, we're changing the bonds. So we're changing the potential energy. What phase change, if any, is occurring at this segment? Solid to liquid. What do we call a solid to liquid? Melting is the layman's term. Anybody remember the chemistry term for that? What's the chemistry term for melting? It is fusion. What equation would we use to determine the energy being absorbed here? Can I use Q equals MC delta T? Why not? There's no change in temperature, so the delta T would be 0, so I can't use that. What's the other equation that we gave you? It's Q equals M delta H. Now remember, on your homework sheet, somebody took all the deltas off for some reason. I don't know why. So the one you guys did last night, it said Q equals MCT. And the one that's assigned for you tonight says Q equals MH. It's actually Q equals M delta H. Delta H is enthalpy. Okay? So if we know that we're using Q equals M delta H, I'm going to look up here and see my delta H of fusion, because that's when it's changed. That's the phase change we're undergoing, is 333 joules per gram. The mass was 100 grams. The mass does not change just because I'm changing phase. So 100 times 333 moves the decimal 2 places to the right to give us 33,300 joules. Now here's the important question. What is the significance of the temperature 0 degrees Celsius for water? I'm going to be specific on this. I know it isn't specific on yours, but specifically, what does 0 degrees mean for water? What if the energy is being released? What would it be doing at 0 degrees? We say it's the melting point or the freezing point. It's both. Melting or freezing. Is everybody cool with that? All right. We're going to flip over to page 19 now. In segment C, What phase or phases are present in segment C? So what phase is water in from 0 to 100? It is in the liquid state. Is the energy absorbed from the heat source changing the water's potential energy or kinetic energy? It's kinetic. How do we know it's kinetic again? Beautiful. You guys are starting to catch my pattern. This is starting to be nice. All right. What phase change, if any, is taking place in this segment, in segment C? There's none. No phase change there. So what equation would I use to determine the amount of energy absorbed? Say it out loud, Griffin. Q equals MC delta T. And you'll notice I put the values in there. The values is 100 is the mass. The C for liquid water is 4.18 joules per grams degree Celsius. And the delta T is 0 to 100. So 100 minus 0 is 100. So I'm taking the 4.18 and I'm multiplying it by 100 twice. So that means I'm going to move the decimal a total of 4 places to the right to end up at 41,800 joules. Everybody cool with that? Now we go segment D. What phase or phases are present in segment D? Liquid. What is there any other one? Liquid and gas are going to be present in segment D because there's a phase change happening, right? Anytime there's a phase change, there will be 2 phases present. Is the energy absorbed from the heat source changing the water's potential energy or kinetic energy? Potential. Why is it potential? No change in temperature. Beautiful. What phase change, if any, is taking place? Keep it up. You're saying it. You're not even making the mistake. It's vaporization. The biggest mistake people will say is evaporation. But remember, evaporation can occur at any temperature. Okay? They're essentially the same process. It's a liquid turning to a gas. But vaporization is specifically at the boiling point. That's kind of important. Okay? What equation would I use to determine the energy absorbed? Q equals M delta H. Which delta H are we going to use for this? Am I going to use the delta H of fusion? No, I'm not going to use the delta H of fusion. I'm going to use the delta H of what? What's my phase change? Vaporization. So I will be using the delta H of vaporization. What's my mass? Did my mass change yet? No, mass doesn't change. That would violate the law of conservation of mass or matter. So the mass has to remain at 100 degrees or 100 grams, excuse me. So 100 grams times the delta H for vaporization, which is 2260, means I'm going to move the decimal 2 places to the right to get 226,000 joules. So what does that tell me? Is it a lot of energy required to become a gas or a little bit of energy required to become a gas? So when we're doing those LOL charts, you should see why is it that I'm going straight from 2 blocks in the EPH to 4? Because there's a lot of energy that I have to get to go from that liquid to a gas. A lot of energy. Does that make sense, everybody? Okay. What is the significance of 100 degrees Celsius for water? It is the boiling point. That's where water boils. Now, could we call it the vaporization condensation point? Sure. But it has a very specific one that's different than all that. So we stick with boiling point because anytime I have liquid water at 100 degrees, it will be boiling. Yes, sir.
What was the significance of the temperature for 0 degrees Celsius?
That was the melting freezing point. That's where the mistake came in here. Was I said what was the significance of 100, and they immediately went to the phase change. But boiling point is like that's where the phase changes occurs, but it has a special thing because it's doing something that water doesn't do any other place. You can see something occurring. Okay. All right. We're on to segment E. What phase or phases are present in segment E? It's a gas. Just a gas. Is the energy being absorbed from the heat source changing the water's potential energy or kinetic energy in segment E? Kinetic. Why is it kinetic? We're changing the temperature. Outstanding. What phase change, if any, is taking place in segment E? I didn't hear you. It is none. Great job, Manal. What equation would we use to measure the amount of energy absorbed? Say it out loud. Be proud of that one. You got it. Q equals MC delta T. And again, I put the values in there. In this case, the mass is still 100, but the specific heat of steam is 101.84, excuse me. And this delta T is going from 100 to 110. So 110 minus 100 is just 10. So I'm going to take the 1.84 times 100, that moves it 2 places to the right, times 10 moves it 1 more place to the right to get 1,840 joules. Anybody have any questions on this so far? So now comes the big question. What was the total amount of energy that it took to take that block of ice at minus 10 degrees Celsius and raise its temperature to 110 degrees Celsius? We just found the amount of energy for each segment. So to find the total amount of energy to complete that process, you add them up. Segment 1 was 2,090. Segment 2 was 33,300. Segment 3 was 41,800. Segment 4 was 226,000. Segment 5 was 1,840 for a total amount of 305,030 joules. That's the total amount of energy it takes to raise the temperature of a 100-gram block of ice at minus 10 all the way to 110 degrees. And you know this would have to be in a closed system, otherwise we would lose some of our gas. Everybody with me? All right, turn to page 15. That's where your homework is for tonight.